during evacuation, tolls are suspended. So you're increasing the infrastructure's capacity to move vehicles during those things. So those are huge. I mentioned before the 1950s bridge that is currently in operation is nearing the end of its service life. The new bridge we're building will be much more resistant to saltwater corrosion, because that's really the reason that the older bridge is deteriorating at the moment. I mentioned the bicycle and shared use path. That's a unique feature. I'm going to show you guys some pictures of what that's going to look like. And then the express lanes, which accommodate different modes of demand, whether we have managed with dynamic tolling or provide BRT in those lanes. And then we mentioned the future transit. So that's really the big scope of what we're trying to accomplish with Howard Frankland. All right, so to give you guys an idea, I'm sure everyone on this call or in this room has driven over this bridge. The corridor that we're constructing is about 7 miles long. The bridge itself is about 3. So of that bridge, you have the bridge in the middle, and you have causeways on either side of the bridge. So we're widening both the bridge and we're widening the causeways. You'll see that here in a minute for a place for the bridge to land. But this gives you an idea. It's pretty much encompassing all the land, the water and land mass between Pinellas and Hillsborough counties. All right, this is a typical section of what the bridge is going to look like. As you can see here, this is a very busy structure. Going left to right on the outside of the bridge, which is the northernmost side, is our shared use path. The replacement of the 4 general use lanes with full width shoulders. So basically replacing what the current southbound bridge has. And then you can see we are operating with barrier separated express lanes, and those will be in both the north and southbound directions for now. The innermost express lanes, so the lanes most on your right, are the ones that are being constructed such that they will carry a future light rail. So you can see the beam spacing is a little closer, and the deck is a little thicker to ensure it has the structural capacity to do that. It's a very wide bridge. It's 168 feet wide. It is the second widest bridge in the state of Florida. The only bridge that's wider is a little heavily skewed box culvert down on the turnpike. So I'll say it's the widest bridge. It is the largest bridge by deck area. There is no bridge in Florida that has more deck area than the new Howard Frankland Bridge will when it's complete. Almost twice the amount of the Skyway Bridge. All right, so just a couple animations here to help you guys understand the sequencing. Here's our current situation today. Like I mentioned before, you have the bridge on the right there that says 1960. Like I said, late 50s, 1960 when it was constructed. That carries northbound traffic to Tampa, and the 1990 structure that carries southbound traffic to St. Pete. So we're building the new bridge off to the north. So we're depicting here the typical construction method they use. Again, this is not what they actually built. This was prior to the project being let. So as we add on and construct on the north side, we'll eventually complete what we're calling the 2020 bridge. Well, hopefully the 2024 bridge when we get it open this year. And once that bridge is complete, the first movement that we will change is the existing southbound movement. So here you can see traffic is moved on to the new structure that's carrying the southbound main line and the north and southbound express lanes. The bridge in the middle, we're doing some rehab on it. It's in good shape, but while there's traffic off of it, opportunity to fix some joints, upgrade some lighting, things of that nature. So traffic will run on the old bridge until that point. Then we'll move the northbound traffic to what was the southbound bridge. And then eventually at the end, we will demolish and recycle the old bridge. So the whole corridor will shift to the north slightly. So let's talk a minute about bicycle pedestrian accommodation. So transportation, like we said, has changed a lot. We want to provide access as the DOT to all modes that we can. And we also know that regional trail connectivity is there's a big push for that with micro-mobility and things of that nature. So Howard Frankland Bridge does its part by connecting existing bike facilities on the Hillsborough side. I think it even connects up to the upper Tampa Bay Trail and takes those another option down to the Pinellas side. Once we interface on the Pinellas side, there's going to be options for connectivity going west along Alberton Boulevard, the middle of the middle diagram there, you can see that, or going south along 4th Street to St. Pete. So again, for this provides other options for even commuter options for bicyclists and things of that nature. All right, so just focusing a little bit more on what that looks like. The shared use path will be rather a minimum of 12 foot, 12 foot wide, obviously meet all ADA requirements. And we will, it's going to be barrier separated from the roadway. So it'll be a safe path. But you can see here just the variability that we've got in the width a little bit, 12 to 13.5 feet, and how we would snake it along the existing vehicular lanes. All right, so another feature, again, like we talked about, was the express lanes. So our express lanes, one of the reasons they work so well is they have fewer ingress and egress points they're more for long regional trips rather than exit to exit. So with that, we do have some entry and exit points for our express lanes on both sides of the bridge. And all with the department going to all cashless tolling, our toll gantries are important to, actually, I take that back. This is not that slide. This is how we're gonna weave the bike ped bridges over the access road. So Howard Frankland's got FHP turnaround points, that red, those little red roads that go underneath for U-turns, for official use only. And this just shows some grade separation as the shared use path won't have to conflict with those vehicles. Apologies, I was looking at the wrong slide. All right, so knowing the bridge is long, we did want to provide some of the ability for like multimodal users to have some rest while they're traversing the bridge. As part of the construction, we're constructing 4 scenic outlooks. So this is a depiction of what that system looks like. On these, we had a vote for the aesthetic features. We went with marine theme, so sailboats, and we sent a vote out to the community regarding the shape of the sails. So 2 main, Marconi sails, schooner sails. Marconi sails won out. As you can see, I think it's a pretty neat little rest area if you're traversing over the bridge and you want to take a break. So we're excited about incorporating some of those aesthetic features into our bridges. The way Howard Frankland is not a signature bridge, the way the Sunshine Skyway is, but it's still a high visibility enough that it deserves an aesthetic treatment. All right, so in the future, what would a light rail system look like? This is just a prettier version of the typical section that shows when we're open later this year what the configuration will be with the express lanes in both directions running on one bridge. So the idea in the future, if the region were to decide to construct a light rail system, we would take the northbound express lanes, like I said, and convert those to fixed rail. And then we would have to widen the 1990 bridge to accommodate the express lanes, and there'd be the northbound express lanes would sit on their own structure. So no real plans for that yet, but we definitely want to make it possible in the future to do that as cost effectively as possible. So that is the plan for light rail. What would that look like? Obviously, functioning on a concrete bridge deck, we're not going to use ballast. So instead, we'll have rubber boots with a tie block system that's anchored to the concrete. One of the things what's interesting on this job was, in case it were to be an electric type rail, that you have to isolate stray currents through the bridge. Those could potentially cause corrosion. So we continuously grounded all of our rebar in the bridge there to avoid that from happening. Information there on the loading as far as rail definitely has a higher loading requirement than trucks or typical design vehicle for a roadway. But here you can see we're designing right now for a diesel engine, a little heavier, but it could potentially also be an electric system depending on what ends up getting built in the future. To be clear, this is not Brightline. This is not heavy gauge track. This is more of your either rubber tired solution or some sort of light fixed guide system that we could potentially install on this bridge. Right. Focus on the causeways for a minute. As you know, you guys probably saw the news with Hurricane Ian and what happened with Sanibel. Interestingly enough, our causeways are more vulnerable to storms than our bridges are, generally speaking. So we did not want to ignore the ability to have a bridge, or damage to our causeway while we're building the bridge, and it'll be, resilient, but we want to make sure our causeways are too. So we're incorporating several features that will help increase that resiliency. So one of the things we're doing whenever we install this, like the seawall, like you see here on this bridge, all the reinforcement in it will be FRP. We will not have any steel reinforcement in any of these elements. The reason for that is saltwater corrosion, and theoretically, these should be, able to survive for perpetuity when it comes to saltwater intrusion, just given the exposure of them. Our MSE walls, as our approaches to our bridges, will all use non-metallic straps. That's pretty standard for the environment that we're in. And then as we're constructing the seawalls are going to go deeper. The idea there is to avoid any concerns with scour. That was the challenging thing for this project. Was some of our most pristine seagrasses in Tampa Bay are located just adjacent to this bridge. So we had to build those very, very carefully and make sure we permitted any impacts and restored them appropriately. All right, just a couple of other lessons learned from Sanibel. These two details, the one on the left at the bottom there shows a protection of MSE wall. And again, if you go out in Sanibel, you'll see those MSE walls just failed spectacularly. That was the real problem there. So here you can see we have a shield barrier concrete in front of our MSE wall that's tied into a marine mattress, which is some fiber reinforced concrete. That's again for the north side where we have a higher profile in MSE wall. On the south side where the existing bridge is at grade, we are doing some very large riprap with marine mattresses. It's very similar design to how they're restoring Sanibel. This should be much more resilient in the face of a storm. And I can show you guys, and you'll see a slide in a minute, just how vulnerable to waves this roadway is. All right, talk about roadway geometry for a minute. Obviously, the bridge is straight. There's no horizontal geometry concerns except for a slight curve on the west side. Our vertical grade is a 2% max, so pretty high design speed, low K value. High K value type of vertical curve here. The navigation clearances, we're still matching the 75 feet navigation clearance from the 1990 bridge. In this picture, what I tried to describe here is when it comes to height of the bridge, there's about a 10-foot difference between the 1960 bridge and the new bridge. And so this picture is the best example I could show you. The 60s bridge had a higher percent slope. You can see there that bridge to the furthest away is the most, has the highest curve. And then you can tell on the bottom there, those piers are higher than the existing deck of even the 1990s bridge. The reason we're doing that is, again, for protecting the bridge from storm surge plus wave action. We had a failure many years ago in Pensacola where a storm came in and took bridge spans right off their foundations. So that's one of the things we're doing here, again, anticipating a very long service life for this bridge. As well, we're incorporating a new fender system. And again, here for resiliency, these fender systems are notorious for maintenance with corrosion, as well as getting struck with marine timber. The system that we're using now is going to be all thermoplastic. So it'll be a fully resilient system with really no vulnerability to saltwater corrosion. In addition, this used to be a navigable waterway. It's really not anymore. So personal boats, recreation boats will only be the ones that use this. But we wanted to be prepared to provide that service to the boating community. All right, so I know early on there was a question asked about some geotech concerns on this bridge. The hardest part of this project has to do with the geology beneath the bay. So beneath the bay, you have a pretty constant depth in the bay. The depth's pretty shallow, 8 to 10 feet roughly. But what you have is you have varying levels of sediment, and you have pinnacled lime rock beneath that. So if you were to drain the water, take off the sediment, it's going to look like a mountain range down there, pretty much. So we were aware of this from construction. We built 2 bridges right next to it. We know that this was definitely a concern. So what do we do about it? A lot of testing. This was some unique testing we did here using some tomography with P waves. You can see here in this picture, this was a P wave refraction that's supposed to tell us the interpreted height of the lime rock along the, did this in 3 lines along the alignment of the bridge. So of this, we were able to get some diagrams here that will show you the possible depth of the rock. Now this is at the very Pinellas end, and the geology changes as you get closer to the Hillsborough side, and you'll see that here. So in this, you can see, according to this, we have some sections that are as low as 45 feet and some sections that are as low as 90 feet. So we're already encountering a large amount of theoretical variability. That variability continues as you move further to the Hillsborough side. So here, as you can see, this is 60 to 80 feet. And then as you come closer to the Hillsborough side, we start to see a little more shallow lime rock. And then eventually on the Hillsborough side, it becomes very, very consistent. So that's good news. But the bad news on the Hillsborough side is the type of rock they encountered was extremely hard. It's the hardest sedimentary rock that I think there is, chert. I'll have a picture of that in a couple minutes. I'll show you guys. So someone asked the question about when you drive the job, you'll see we have our piles that are sticking up out of the ground. And it would appear there's no real rhyme or reason to why some piles have 20 feet sticking out of the ground, some of them have 5 feet sticking out of the ground. This slide will hopefully explain a little bit as to the why. What you're looking at here is on the horizontal axis, we have the piers of the bridge. On the vertical axis is the elevation. The blue line shows you the shortest pile on a particular pier, and the yellow line shows you the deepest pile in that same pier. So for instance, if you look on this, you get right there between 37 and 42 east, you have a pile that goes all the way down to 175 feet, and you got a pile that took up at 95 feet. So you're talking about 100 plus feet of variability, which this was the existing southbound bridge. We're experiencing this and more on the new bridge. You could have a pile that you drive between here and the other side of the screen. Vertically, they'll vary more than 100 feet. That's how variable the lime rock is in that environment. All right, we'll talk about tolling now. This is where I thought we were at. So again, express lanes require a thoughtful placement of ingress and egress points to maintain service levels, as well as putting spots where people could potentially enter and exit them. So we do have 2 entrances for the express lanes in Howard Frankland on both sides of the Causeway, and each of them carries a gantry. So I think I mentioned before, all of this will be electronic tolling. We're going to a full cashless system with a SunPass, and there's an infrastructure that's required to ensure that stays up and operational in a rather difficult environment. So here is the Pinellas side. The purple shows where the gantry will be, as well as the maintenance building. And then on the Hillsborough side, this shows you the entrance from the general use lanes for southbound, and then where the gantry will be for the variable tolling on that. All right. Wanted to talk briefly about, as we've done with the design, how do you get from design into the ground, right? So a job like this, you have to hire a contractor. And so we have a lot of options in the toolbox for procuring contractors for our jobs. This particular job is a adjusted score design build. So most of our larger jobs go design build for a number of reasons. Wanted to talk a second about the process for developing an RFP for design build. is basically we tell the contractors what we want. This RFP said we want to construct this new bridge, we want it to have these features, but we don't provide them a whole lot of guidance otherwise. It's up to them to provide us their solution. And one of the things that we want to see as part of that is some innovation. The idea, if you put it in the hands of industry, you're going to get more creativity than just an owner who might be focused on one particular design. So on this job, I think in the beginning we had, I think, 3 or 4 firms who were interested, submitted letters of interest, and then we had 2 firms that moved forward to a technical proposal. So the team that won was Archer Western. They were a joint venture with Traylor Brothers. Traylor Brothers ironically built the 1990 bridge. So they teamed together, and the other company we had that proceeded forward was Granite. Archer Western and Traylor Brothers won. And when I say win, what I mean is the way you win a job in a justice score design build is not just price, not just low bid. You could theoretically win without being the low bid because there's a technical score component too. If your job is if your proposal has more features, you still could get awarded the job even if you're not the lowest price. We call that a best value selection. The benefits of this process, there's really 3. I mentioned the one previously. More innovation, you get different teams proposing different ideas. We have a whole process for that I won't get into. Another one is a risk transfer. So a job like this is, like I said, $866 million. If you don't design it and there's an error, you don't have to pay for fixing that error. That risk falls onto the contractor. So there's a little more price certainty for the department there. And then you increase the speed of construction, because if you did a bid build job, you'd full design, procurement, and construct. On this particular one, you can procure, design, and construct all at the same time. The other thing I'll mention here, the design EOR for this project is BCC Engineering, and our CEI is Atkins, is our prime CEI. All right, so where are we at to date? Right now, the project is, we just achieved a milestone of completing all of our piles. So over 3,000 piles have been put into the ground. And these are not small piles. These are 30-inch concrete piles. It was a lot of work. Our substructure is very nearly complete. So our footing is 93%. I want to say the bridge, I think it's about 140 spans. And then about 90% of our bridge columns. Then you move up to caps. And then our decks are really the main thing you're going to see being built right now. So just to give you an idea of the breadth of this job, you have, again, almost 7 miles, 107 football fields. The bridge deck, like I mentioned before, is the largest in Florida, more than double Skyway. And those bridge piles, you put them end to end, you're talking about 40 miles long. That's from here almost down to Bradenton. So a lot of embankment, a lot of concrete. It's a very big project. The nice thing about it is it's repetitive. So the contractor has gotten very good as he's built. It's like building 140 mini bridges. And he's gotten very good at this point and being efficient with his construction. All right, just give you some pictures of how this looks. As you can see, what this is showing you is the Hillsborough Causeway. Because we're building the new bridge to the north, we had to widen the causeway to receive those lanes. And that's what you're seeing here is the construction of the embanked area with the seawall caps that are being built. You can see the concrete off to the on the picture to the right, off to the left of the left of that picture. So that's really gives you an impression of what is going on. What was going on there. This is a picture of our substructure construction. What I want to mention is, as you guys have driven past there, you see there's a ton of barges, there's a ton of cranes. We have logistical challenges to ferry all these people to these work platforms and then actually move the equipment to where you need it. That in itself is a small miracle, much less actually building the bridge. So here you can see some of the work barges that are set up. On the left is some of our, we're getting ready for our pier cap pours. So you see here we have our formwork and then the columns to the middle there. And then you can see on the right kind of our completed hammerhead piers, just kind of some twin structures, really trying to match the aesthetic of the 1990s bridge. And you can see here that we're matching the span lengths of the 1990s bridge as well. So some more aesthetic continuity will also help boat traffic traveling underneath the bridge. The old bridge did not have the same span length, the 1950s bridge. Here is a picture of beam placement. So again, you have a barge that has all these beams, and you've got this big red-yellow crane. That's our ringer crane. Another fun fact is that crane also flew all the beams for the 1990 bridge. So that's Trailer's crane. It's built this bridge twice. It's a pretty neat piece of equipment. But you can see here flying the beam lines and setting up for that, and then afterwards you see the deck placement. So here's a good idea. You see on the very right the stay in place forms, the next one a cured deck, and then you see where they have the burlap or the visqueen over a deck that's currently curing. The contractor is using a bidwell system to construct these. He is building this deck in 2 phases. You can see where that crane is standing. That was the deck for the light rail. That was a thicker deck. He's constructed that first, and then using that as a work platform to build the remainder of the remaining width of the deck and pouring that span by span. And I'll show you how they're doing that in another slide here in a minute. All right, so on the Pinellas side, I think I mentioned this project interfaces with our Gateway construction project. So again, on the picture on the left, you have a widened causeway to receive those new lanes. And you can see here at the very top of that picture, we have our traffic further to the west is shifted into its final alignment that allows the contractor to build the median where the express lanes will eventually go. And then on the picture on the right, that's a picture looking northeast. You see 4th Street, the new flyover bridge that we're nearing completion on. But this is the tie-in to Gateway. So it really gives you an idea of how continuous this construction is going to be once it's complete, or the project will be with Gateway. All right, so getting to some challenges. The picture you see here is that chert I was speaking about. So this was what was found on the Hillsborough side. The contractor had a very difficult time driving pile through this. He had to basically drill through this layer. Otherwise, he'd be breaking piles left and right. That to keep the schedule, they had to drill 24 hours a day for several months, and they only recently got through their last layers of that. So you can see that almost looks like quartz. Very hard material to drive through. Very, very expensive operation, but they were able to overcome it just by brute force, and glad to have that behind us. Next one I'd spoken about before, the pile variability. I think that sheet showed you on the old bridge, we had a pier that had almost 100 feet. On this one, we're nearing more like 170 feet of variability in the same pier. Why is that important? You know, contractor has to pick a particular pile length that he uses for a particular pier. And if he has to drive, he has to splice it, has to drive further. So that could be a potential delay for him. So that about 10% of the piles on this job had to be spliced. And that was one of the biggest risks the contractor had to take on. Drilling through the chert, like I said, was a very difficult thing to do. And I'll talk about on a future slide, the MSC wall aggregate design change that we made as a result of Hurricane Ian. So in this job, we had a lot of environmental permits that we had to comply with. I think everybody, we had to get a permit from basically every federal agency that governs anything over the water: Coast Guard, National Marine Fisheries, SWIFMUD, DEP, you name it, we had to get a permit. So some of the things that were unique on this was the quiet zones for pile driving. We were required to keep about 1,000-foot exclusion zone between our pile driving operations. The idea there was the sound waves from the pile driving would affect the fish, and you wanted to give them an ability to marine life to pass through the work zone without, incurring that damage. The American oyster catchers, the picture there on the pictures on the right are the little protected birds that decided that nesting in our embankment areas would be a good idea for 2 years in a row. A big challenge to work around them, but both times that when they nested, that we can say successfully that they hatched chicks, and they left, and we were able to resume construction. So it was a win-win for everybody. They're cute little birds that don't actually eat oysters or catch them, but they're called oyster catchers. Manatee watchers, anytime we have a barge movement during pile driving operations or anything else, we're required to provide watchers to ensure that we're not impacting manatees if they're going through our waterways. And then for water turbidity, we had to maintain a 500-foot mixing zone. So obviously to keep the bay water pristine. So a lot of restrictions there, but we were able to really, I think, overcome a large number of those very easily. So this was probably the one that's a little more challenging. The picture on the top left was during Hurricane Idalia, the storm that passed to our west. And in those cases, that's the most dangerous storm for us because it pushes water up the bay. So if you remember that day, we had water completely overtopping the northbound lanes. And that wasn't even as bad a storm as it could get. So there's an example of why we're doing all this hardening on our causeways. During hurricanes, the contractor is required to move their barges to make sure that we don't get any damage to our bridge. So you can see their picture in the bottom middle is what they call their barge island. This is where they will take their barges during a storm and protect them. And they have an entire plan, 72 hours before a storm gets here, what they're going to do to protect it. Contractors have been really good to work with on this, and I'm glad to say we haven't had any incidents, or really even with the storms we've experienced, really even lost any equipment as a result of that. Another thing, on either side of Howard Frankland, we have two major airports. Airports and cranes typically, they don't mix. So we've had to work with them, make sure we abide by the airspace restrictions. There's required restrictions for drones and things like that. And that's just something to point out. Logistical challenges, like I said before, you have a marine fleet that at its peak was 60 barges and 30 cranes. And as far as labor required to build this, you're probably looking at about 300 craft laborers to construct this project in the time frame that was allowed. They're still close to 300, but the job, now that pile driving is over, is on its way down. Supply chain, we've been really fortunate on this job because of the size of it. It has garnered the attention of a lot of our suppliers who have been maintaining their supplies. So things like embankment for the causeways, concrete. We have our precast concrete elements. We've really worked well with our partners to ensure that we get the supplies that we need. And then this job was let before COVID. So all the inflation and stuff that's happened since then has been a big challenge for the contractor to work around. I almost finished. A couple more slides. Resiliency. So one of the big things that we had talked about, I want to show you all a picture. This is the end bent in our MSE wall, where the two pieces of equipment, the roller and the little tractor is there. That is all 57 stone, so that's coarse rock. And the reason we put that there was because that would drain much better than embankment. Now, again, the failure mode of Sanibel was the MSE walls blowing out due to lack of drainage through the backfill. So this is one of the ways that we're finding that we can protect the embankment area as well. I won't go too much over the other improvements we made, but like I said, we're doing marine mattresses, riprap, and we're setting the bridge elevation so that it's 1 foot above what we think the worst case wave action would be if we got a 100-year storm on coming up to Tampa Bay. So here is just we have a model that depicts wave heights for that 100-year storm. You can see there we could anticipate up to 18.5 feet of water rising between storm surge and waves, and still would be below the bridge. All right, just a couple more innovative features. One of the things that they did on this job was 100% PDA. Usually you have to drive a test pile and then get a production depth and drive from there. PDA allows you to immediately know your capacity of your pile. And on a job with 3,000 piles, it's pretty important to keep your schedule to be able to rely on the increased capacity a PDA gives you. I'll show you a picture of the conveyor system, how they're pouring concrete from the existing bridge. It's pretty neat. We talked about the shared use path and then the aesthetic features on the scenic overlooks. Dropout forms, and again, this is one of the innovations you get from a contractor who does the same type of work over and over. Our hammerhead caps, instead of building the forms, what they had reusable forms, and the bottoms would drop open, so you could just pick them. You could pick them right off. So again, something that might take a week to dismantle, they found a way to do it in a day. So there's little efficiencies like that they're able to do. Pile cutoff saw. This is neat. Again, when you finish driving, you might have piles that are 20-foot excess for cutoff, some that are 5. Pile cutoff is one of the most dangerous operations in marine construction, really any bridge construction. So they developed basically a robot that was had almost like a bandsaw that would just automatically cut through the pile without anybody being anywhere near it. So much safer and much quicker, much more reliable. So quick picture of the pile driving. I'll just skip through that. Here's the conveyor system. Is like I said, they pour concrete from the existing bridge where the traffic shifted on the southbound bridge, and they'll convey it over the water and pour it into, you can see there on the left where the bid well is running, and pouring that deck. That's worked really well. We cast all our bridge decks at night because of humidity, and that's a good thing. So just at the end, quick plug. I was thinking this morning, there's not many engineers who get to work on a almost $1 billion job in their careers, right? And our office has several of those projects going on. So wanted just to do a quick plug for, DOT is a great place to start a career. We have 2 opportunities depending on where you're at in your education. If you're still in school, we have internship opportunities. And then we have, if you're a recent graduate or a soon-to-be graduate, we have some stuff here we'll share on our PE training program. That's how I started with the department. And it's an excellent opportunity to really just get exposure to all things transportation. DOT is a big owner. We get our hands in a lot of things, and it's just a neat opportunity. So really appreciate your time today, and I guess I'll turn it back over, and we can entertain questions or anything.
Thank you, Gray, for your great presentation and introduction about this bridge project.
Thank you.
So we'll leave the floor to audience for any questions or comments. So for those of you online, if you can just unmute yourself and ask us a question, or you can just type your question in the chat.
Hello. Thank you for your presentation and coming here. So my question, I have seen some conceptual design of bridges when they consider some green elements, some like trees, bushes, or grasses. I mean, I never seen something done, but I was wondering if it is possible for this project to do some green adding some green elements to the bridge, like trees, bushes.
Yeah, no, that's a good question.
It is considered or not.
Yeah, I've seen it too. The challenge becomes there. It is possible to do. The challenge becomes there is one of maintenance, right? Is that if you have a bridge that's that far over water, how do you get fresh water to planters or things of that nature? So it'd be finding a maintenance partner to do that, and then really the cost of keeping that, looking good. So we do a lot of our jobs do incorporate a landscape. You'll see most of our interchanges have, rather postcard-esque type, big palm trees and things of that nature. But we tend to shy away from doing that on bridges just because of how difficult it is to maintain. Good question.
Where is the bike ped connection on the Hillsborough side going to be?
So what it's going to connect to is the east-west portion will connect to Rio Street, and then Rio Street will provide a connection north up to Cypress. And I think it ties into, I forget the name of that trail, it ties into an existing trail there that runs up toward Courtney Campbell and eventually to the upper Tampa Bay Trail.
Okay. I noticed I was driving past on the existing Howard Frankland a couple months ago because I had to take the P exam, and I noticed as I was driving past it, it looked like the bearing pads on the Howard Frankland that's about to be constructed were all deflected. At least on some of the spans, it looked like they were deflected. I don't know if that's a challenge that you were facing right now.
On the new bridge?
On the new bridge, yeah.
Yeah. So depending on those things are designed to move. I think these bridges have 143-foot span. So I don't know how deflected they were, but there's two explanations, right? They were either placed on the wrong spot, or I don't know if it was a cold day where you had shrinkage and you actually had some bending in them. But certainly, I can't speak to exactly what you saw, but
it was more than what I was expecting. I guess when I was driving past it, it was noticeable from the existing bridge. I was like, whoa, it's kind of a lot of deflection. But
yeah, I have to look into it. But yeah, you're right. I mean, when they set those things, they're supposed to set them to where you're right in your mid-range of temperature to keep them somewhat perpendicular.
Thank you. It was a really good presentation. Also, thank you.
Appreciate it.
We do have a comment from the online audience, but I guess she kind of provide the answer. Hui Qing, do you still have that question? Basically, she asked about the criterion for bridge surface friction in order to identify, evaluate, or plan safety enhancements.
Bridge surface friction.
Bridge surface friction.
So, yeah. So DOT. I mean, all of our bridge decks are concrete, and so once we what the process is on bridge decks is we will grind them, and we'll in the same time we will longitudinally groove them. And so that groove surface is what provides our friction in wet weather driving. And then we'll make sure the other aspect of that is our slopes, right? To make sure that we either have scuppers collecting water before it sheet flows, down a certain distance to prevent hydroplaning. So those are the two real features that we incorporate on concrete bridge decks for skid resistance.
Right. I noticed that from your typical cross section of the bridge, as the cross slope is like 3% for the general lane, and higher than, I forgot the number, higher than 3%.
Yeah, because we have multiple scuppers.
Yeah.
So each at that barrier wall will collect it. So you won't have to worry so much about it sheet flowing over several lanes and maybe causing a hydroplaning concern. That's a good question.
Thanks. Let's see if there's any other question or comments from the audience here or online. Let's see any. I have a question. I see the piles, the longest pile can be like 180 or 200 feet. I'm kind of curious, how are they like a long pile, like driven in sections?
Yeah, so what'll happen is most of their piles that they've cast are roughly about 90 feet in length. It varies somewhat, but that's generally their design length. And so what'll happen is as they're driving and they're doing their PDA analysis, they'll be able to tell if a pile is going to pick up capacity or not. And so if it doesn't, what they do is they'll stop. And so there's it's called a set check. So if you stop driving and come back a day later, it might take up and you don't have to splice it. But if it doesn't take up, then they'll have they'll build in a splice plate, and they'll actually physically connect another section of pile on top of it, and they'll continue driving as though it was new. And so I think the longest pile we had to do that, we had 3 sections that we had to splice together.
So how are the sections of pile connected?
It's a doweled in,
okay.
a dowel connection, a
Okay.
mechanical connection.
Okay. All right. Thank you.
Welcome.
There's one question. Actually, there are 2 questions. First question is the pile in this project precast instead of cut? I mean, you can answer that. Cast in place. Is this for technical aspect or saving construction time?
So these piles are pre-stressed. So the only real way to make pre-stressed piles is to precast them.
Precasting.
So we have all of our foundation piles are precast, as well as our beams. All the other foundation components, those are all cast into place. But it is possible to precast those elements. And yeah, precast is they do it really for speed, and you get a lot better quality control in a shop than you do on casting in place.
Thank you. There's another question from Daniel. The question is, how are third-party inspections conducted for bridges? Or on-site? Or
I'm sorry, say that.
How are third-party inspections conducted for bridges?
I heard inspection. I didn't hear what type of inspection.
So the third-party.
Third-party inspections. Okay. Yeah, so we have a company that oversees all of the construction on the project. Our CEI stands for Construction Engineering and Inspection. So they're an independent company that the department hires to oversee the construction. So they have, on any given day, between 20 and 30 people out there inspecting the work. So they'll inspect, things like the rebar placement. They'll take samples of concrete to have cylinders broken and tested. They'll take samples of embankment to make sure it matches all the criteria. And basically, they're also there to overcome any problems. So these contractors know that there's certain elements. We have what's called QC inspection, their own inspection. And then we have our independent third party, our VT inspection is what we do. So that's what my office primarily does, is inspection of these type of projects.
Thank you. Okay. All right.
Hi, a very nice presentation. My question is about the scenic overlook. So if we can just go back to the slide, I love the design, but I was just wondering, is there any provision, like if a bicyclist or pedestrian, they're on their way and it started raining, is there any provision to, protect them from such weather conditions?
Yes, you see the concept there does show like some bench areas that have some sort of sheltering. So the idea would be that they could go under that if they need to. But yeah, that is something that we want to consider.
Thank you. I have another question. So I was just wondering, this is like from my personal experience. My father just started working. It's like a pavement job, and he deals with a lot of contractors, and he faces a lot of challenge. So I was just wondering what it is like to work with contractors. Like, are they diligent? Are they notorious? What's the delay because of them?
No, it's a great question, because we definitely, contractors are different than engineers, and then we have a lot of contractors who are engineers, so there is overlap there. But I think really the thing about working with contractors is figuring out how do you get to you all have the same goal, right? You want to finish a job, but you have it for different reasons, right? And so it's really work with a contractor. What you have to do is understand what their goal is, and their challenges. They're a for-profit business. They're there to make money, and if they make a mistake, you gotta help them, even if it's not your mistake, and vice versa, right? Because you might make a mistake or might have an error in your plans, and you don't want them calling you on the carpet for it. So it can, there's opportunities for conflict for sure. Contractors, especially low bid contractors, they're not quite as concerned about maybe that sort of interaction. They're more, hey, this is the bottom line. You can help me or you're not. And so I think if you understand that perspective, you do a lot better, focusing more as a partnership rather than an us versus them. But yeah, it can just be challenging, because what you think is the right way to go is maybe a lot different than what they think. But then you always end up coming to a solution and figuring it out. So yeah, it's fun. They don't teach it in school. That's
Thanks for the answer.
Yeah, problem.
Okay, last chance for question or comment. Okay, there's another one actually.
Oh boy.
Which will the FDOT regroove the bridge surface due to poor friction conditions and a high number of crashes, as shown in the previous figures? I mean, she kind of. Where is the figure? Which are you talking? Okay, I think she uploaded.
Did she add something in the chat?
Huh?
Yeah.
Okay, yeah, in the chat, she kind of sent a photo. Probably let me upload.
How to... Ooh.
Yes.
These are friction numbers. So some are like a low friction number 27.
Oh, I see.
Yeah.
Oh, this is on Gandy. Yeah. So, if the question's about the existing Howard Frankland, I don't know what the friction numbers are. I don't think we're scoped to regroove Howard Frankland, the 90s bridge, because I think, once you probably starting about that time, the concrete strength that they used on bridge decks, it just skyrocketed. And so those grooves last much longer now. But I do know we have 275 in downtown St. Pete, where we had we regrooved a bridge that had basically polished. The surface was very, very smooth. We did that. That was probably 4 or 5 years ago, and that was to the point of there was a history of wet weather crashes, and there was also some horizontal geometry, some curves that were a little more challenging than what we have on Howard Frankland. But yeah, certainly I certainly can look into that. But yeah, about the picture shows Gandy, and it makes sense, right? Because you see the bottom bridge there was the older bridge. That bridge was built in the 70s, and then the bridge on the top that has the higher numbers was built in the 90s. So it makes sense that it would have a little higher numbers.
So you mean usually these concrete decks do not get a regrooved that frequently, so they.
No, only I can only think. I'm not saying we haven't done others, but
Okay.
I'm only aware of the one that we've done. And we have an entire safety office that looks at factors contributing to the crashes, and we have a big program to implement improvements. But I think just that viaduct there in front of Tropicana was a candidate for regrooving.
Okay. All right. Thank you.
Okay, thank you.
All right. I think time's up. Thank you, Graham, for your really nice presentation, and also the introduction about the FDOT PE training programs and also the internship programs. Many of our students actually have benefited from these programs. So for those of you who are interested, then please follow up with them. All right, great. Thank you.
All right.
And
Thank you so much.
Great again.